Hi everyone, welcome to CHEM. Now today's video is on chemical kinetics part 7 video. Here we are going to deal with parallel or side reactions, or also known as competitive or concurrent reactions. Now before starting, already 6 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. So let us start. Now in the last video we had already seen how to derive the equations for basically a reversible reaction, right? But here we will consider a parallel reaction to occur. So what is the reaction under consideration? If we have a reactant which is A, suppose this is the reactant A, and we react it in two different pathways. That is, K1 has its rate constant B. Similarly for this one it is C, and it has a rate constant of K2, right? Now we need to understand that we are following first order kinetics. Okay, so at time t equals to 0, we have B, amount of B to be as 0, whereas amount of A to be as A naught, and for C also it is 0. Now when time passes by, let the time be t, then what happens is we have this as, suppose for B it is Y, for this it is A naught minus some amount which we are taking as X, and for C it is Z. And we know what we have to do since two kinetics are being followed simultaneously. So we can write dA by dt equals to dB by dt plus dC by dt, right? And this can be written as K1A plus K2A. And when we take the concentration of A common, we get K1, K2, A. Next step is taking the concentration A on the left hand side, that is this in the left hand side. So let us see. We will write it as minus dA by concentration A, and we take dt at right hand side. So K1, K2, dt. Just what we have done in the previous case. We can take it as ln, that is ln A by AT equals K1 plus K2T. How this is obtained? Through integration, right? So from here we can write AT is equals to A naught e to the power minus K1 plus K2 whole multiplied by T. If we consider this particular thing as a value entity together just like a first order kinetics, then AT can be written as A naught minus X, right? And we can write that this ln versus t graph will be like a straight line passing through the origin with slope which is K1 plus K2. When we draw a graph where ln A by AT versus the time, right? Now we will see the next step what we can do. We can write it like this, that is dB by dt whole divided by dC by dt equals to K1 by A by K2A, right? And this can be obtained as K1 by K2. If we know from here that dy by dt is equals to dB by dt, which is equals to K1A, right? And this K1A can also be written as K1A naught e to the power minus K1 plus K2 to the power t. So from where we have obtained this equation? From this one. From here we can write AT equals to A naught e to the power minus K1 plus K2 t, right? So for dy by dt we have obtained it. Now we need to integrate this equation. So in the next step we will integrate this equation. Integration limit will be from 0 to y dy, and on that side we have K1 A naught integration t from 0 to t, right, e to the power minus K1 plus K2 whole multiplied by t dt. And from here we can write y equals to Bt concentration K1 A naught by K1 plus K2, and this in the bracket we get 1 minus e to the power minus K1 plus K2 whole t. Similarly, if we consider for Ct also, then it will be like this. In place of K1 only, we will write K2 A naught by K1 plus K2 1 minus e to the power minus K1 plus K2 whole t. So you can understand from here only that remembering one equation can help you to find another one. And if we try to divide Bt by Ct concentration, Bt by Ct concentration, we will obtain it as K1 by K2. And T half for A comes to be as 0.693 divided by K1 plus K2. These equations are important, right? So this is one equation and this is another equation. And if we try to draw the graph, which is very much important for this case. So if we have this is the concentration of reactant as well as product, and this scale shows us the time. So for the concentration of A naught, this is the concentration of A naught, suppose. So slowly the graph decreases, right, for the reactant. And for B, that is concentration of B, the graph is like this. It will increase, and this is our B concentration. And for C concentration, it is actually like this, C, right? So these are the terms. Now the important equations for this reactions are this one. First, this is the important one. Next comes our B concentration and C concentration as at time t, and the last two equations which are important for these case are these two. Now from here only we can find out the EACT, that is activation energy or observed total activation energy. Suppose if you consider the reaction to be like this, where B and C is being formed as a competitive reaction. So this reaction has K1 as well as E1 as the energy for this reaction, and K2 and E2. E2 is the energy for formation of C. We know from here that a formula can be derived, which is E observe equals to K1 E1 plus K2 E2 by K1 plus K2. And this equation has a derivation within it. But at this stage, for this video, I will not show the derivation, since we have already not done the Arrhenius equation. We need the Arrhenius equation for its derivation. So once I complete Arrhenius equation, I will show you the derivation of this one. And this much for today. And in the next video, we will deal with consecutive reaction or sequential reaction. So hope this was helpful. Thanks for watching. Do not forget to like, share, subscribe and comment.